Hello, my name is Bodegui. Welcome back to Fractional Calculus. So today we'll be checking the limit definitions for calculus. Now, previous lesson we checked the powers rule for fractional derivatives. So today we'll concentrate on the limit definitions. First, let me have a simple diagram here which will guide us through these limit definitions. So if I have my y coordinates and my x coordinate here, then I have a curve. Again, let me see, y equals to f of x. So to get the slope, or what we call, to get the slope of this function, we have to have a straight line. So I'm trying to get good. Then we have a point here. Let's mark this as point A. So I have to extend this. Then let me extend that. Okay, so I have point, and then let me make this point A, and this other side, marking it down, I have point B. Okay, so if this point B is x, and then from here to here is h, then what do you think our point A will be? I'm sure our point A will be x minus h. That again. So if this is x minus h, that means this point for f or for y, we have f subscript x, f into bracket s minus h, and this other side we're going to have f of x. So that's what we'll be using in the course of these limit definitions. Now our slope, which you call gradient, is the same thing as your f prime of x. F prime of x. So that will be your y2. Okay, let me write this. Your slope is also equals to your gradient. It's equals to your y2 minus y1 over x2 minus x1. So, and it's also equal to your differentiation. So we have our limit h tends to 0. Then we have our y2. Our y2 here is f of x minus your f1, your y1 rather, that is f of x minus h, everything over x2 minus x1, and that is your h. Okay, so that is the first derivatives using our limit definitions. So if we want to go to the second derivative, f prime prime, and that will give us our limit h tends to 0, and our f prime give us f of x. So f prime prime will be f prime of x minus f prime of x minus h over h. So now we need to substitute the value of f prime of, so our f prime of x is given as all this. So we have f of x minus f of x minus h, everything over h, minus, okay, so check here now, we substitute the overall of x minus h to this x, so that we can be able to find the f prime of x minus h will give us instead of this x now we have x minus h. Instead of this s now we have x minus h, and that will give us x minus 2h. So that the f prime of x minus h will give us f of x minus h minus f of x minus h, which will be minus 2h, everything over h. And then we have everything over this previous h. So by the time we factorize it, so we realize that we have name h tends to 0. So this is the common factor of this thing will be h. So the h will meet this h, and that will give us 1 over h squared. Just simple simplification. So here we have f of x, and here we have minus f of x minus h, and here we have minus f of x minus h. That will give us minus 2 f of x minus h, and here we have minus f of x minus h. That will give us plus f of x minus 2h, and that is the second derivative using the limit definitions. So with this now we can easily find our f, the third derivative now, because if we check this, our derivative is following. First, let's check the limit. Here our f prime of x we have over h, one single h. When we have f prime of x we have h, but when we have f prime of x we have what? When we have f prime we have h squared. So that means that our f prime, the third derivative also, that will be 1 over h raised to the power 3, because f prime of x we have single h, f prime of x we have h raised. So by the time we also solve for f prime x, we are going to have h3. So take note of that. Another thing is the coefficient of these our functions. For the f prime of x, the coefficient is 1, 1. So if you remember your triangular Pascal triangle, we have 1, we have 1, 1, we have 1, 2, 1, we have 1, 3, 3, 1. So this for the first derivative, we have our coefficient to be 1 and 1. So the second derivative is here we have 1, 2, 1, which is this 1, 2, 1. Now that the third derivative, we are going to have 1, 3, 3, 1. So let's put that. So we have 1, 1, 3, 3, 1. Alright. So here now, so you will see that it's following a particular line. This is positive, this is negative, this is positive, the next will be negative. So it will be positive, the next one will be negative, the following one will be positive, and the last one will be negative. Alright. So if you also take note, for the first derivative we have f of x and we have x minus h. So the third derivative we have f of x, then the second function we subtract h, then the third we subtract 2h, that is f minus h minus 2h. That means that this our first derivative will be f of x followed by minus h followed by minus 2h followed by minus 3h. Good. So let's rewrite this properly by removing all those coefficient of 1. Okay, we have f prime, the third derivative is named h tends to 0, 1 over h3. So you can just put this in a bracket. Then we have f of x minus 3, x minus h plus 3, f x minus 2h minus f of x minus 3h. So with this now we can write the general formula for the nth derivatives, and let me do that. So okay, we can also rewrite this in using our summation in order to make it more simpler. That is our f prime of x is equals to name h tends to 0 1 over h3. So this we can actually introduce our summation. Whereby we can have k equals to 0 to 3, because that is the highest power. So here now we can see that this is positive, negative, so you have to add minus 1 h power k. So by the time k is 0 we have positive, by the time k is 1 we have negative, by the time k is 2 we have positive again. So this is satisfied. So the next is the coefficient now is following the combination rule. So we are going to have our combination 3 combination k. So when k is 0 we have 3 combination 0, which will give us 1, and 3 combination 2 will give us 3 combination 3, etc., and like that. So that we have satisfied with the coefficients. Now the next thing is the function. For us to capture the function, we are going to have f x minus, we have k h. So that by the time k is equals to 0, so this will be 0, we have f of x which is equals to 0, and when k is 1 we have this term, when k is 2 we have this, and like that. So this capture the whole thing. So with this summation sign now we can easily derive the nth derivative for this particular function. So let's see what that will give us. Changing my pen. So the nth derivative, so we only just have to substitute 3 for n. We are named h tends to 0 1 over h n summation k equals to 0 to n minus 1 k n combination k and f of x minus k h. Okay, where our n is positive integer. So now we want to extend this to fractional derivatives instead of positive integer. So extending n to fractional derivative, it's a real number. So that means that instead of n we are going to substitute it for alpha. So let's see what we are going to have. So we have f alpha x equals to lim h tends to 0. Then we have 1 over h. Instead of n we have alpha, then your summation, we have k equals to 0. Your summation will still be positive integer, and then your k, so you have your n combination, that will be f combination k over f s minus k h. Okay, so but this particular time, this is our combination, we need to work on it, knowing that the fractional combination or the fractional factorial does not exist except we take it back to, except we extend it to gamma function. So I want to work on this particular term, then substitute it back. So let me make this equation 1. So at equation 1 I have alpha combination k, we can also write as alpha factorial over k factorial into bracket alpha minus k factorial. So don't forget your gamma function property. Let me write it at corner here. So you have your gamma x plus 1 is equals to x factorial. So here now alpha factorial, that will give us gamma alpha plus 1 using that gamma property, and this we have k factorial, and this alpha minus k, that will be gamma alpha minus k plus 1. So we now substitute this back to equation 1. So we have something like alpha f of alpha x equals to lim h tends to 0 1 over h alpha summation n k minus 1 k, then we have gamma alpha plus 1 over k factorial gamma alpha minus k plus 1, then we have our f of x minus k h. Okay, so here now I want to introduce this term. Let me call it m equals to x minus a over h, where h represents, where a rather is equals to our terminal point. So in this function, if h tends to 0, that means that your m will tend to infinity. So with that now, making h the subject, we have h will be equals to x minus a over m. So we substitute these two terms. We substitute these two terms in this function. So that means I'm going to have f alpha of x equals to lim. So instead of h tends to 0, we have m tends to infinity, because it wants to introduce 1 over h, that is 1 over x minus a over m. So if we have 1 over this, we're going to have m over x minus a alpha, then we have summation k equals to 0 to n minus 1k, then we have gamma alpha plus 1 over k factorial gamma alpha minus k plus 1, then we have f of x minus k, and your h is x minus a over m. Oh, so I can write this function as d, the operator d, then the other derivative, which is alpha, then the function x, and our terminal point a equals to lim m tend to infinity m over x minus a alpha, then summation k equals to 0 to n minus 1k gamma alpha plus 1 over k factorial gamma alpha minus k plus 1 f of x minus k over m s minus a factorial. So here we have our limit definitions for fractional derivatives, and this function is called Grunwald Letnikov fractional derivative. Or what we call GL operator. So in our next class we will see how to extend this formula and actually make use of it to find the fractional derivative of some certain function. Alright, my name is Sondoluwafemi Godogbe. Thank you for watching. See you in the next class.